I just wanted to add some words to the answer of Professor Petrov to the question about the crack velocity. Actually, we did simulations, and the incubation time approach results in much lower limiting velocity of the cracks.
Exactly.
Contradicting the classical theory. So the incubation time approach actually captures this fact of the lower critical crack velocity, because it technically, I did these simulations. So
I did some simulations too, and it's always like that.
yeah, it's like half of 0.7 at most. So, well, now I go to my talk. It's kind of it's resembling a little the previous talk, of course, because we work with the same group of Professor Petrov. But I will try to give some another angle of view to the problems that are solved using the incubation time approach. So we'll show some very simple and but interesting analogy that we found between the crack initiation and dynamic fracture and failure in some very, very simple discrete systems like linear oscillator. So, in fact, I will talk about two problems and two approaches which are very similar. I will do my best to differentiate them, but they look too close, and probably it would be better to read the papers to get the full idea. So first we will talk about the analogy, and then I will show some very simple methods that can be used to simulate fracture in various dynamic problems, including crack initiation and spallation in rods. So for statics, it's quite simple. We have critical parameters like critical stress intensity factor or ultimate stress, and that's it. You would just calculate fields in the crack tip, or if you have an undamaged sample, you calculate just stresses and you compare them to critical values, and you decide either there is fracture or not. In dynamics, it gets more complicated. The standard route is to introduce some temporal dependencies and functionals instead of critical values. But some experiments, especially with short path slots, can be simulated with using these functionals. And for example, the stress intensity factor can, as Professor Petrov just told us, stress intensity factor can be lower than the static critical values if the so-called fracture delay is accounted for. Means that the load has already stopped, and we are at the decreasing stage of the stress intensity factor, and fracture initiates at this decreasing stage. So, of course, in these cases, classical static and even classical dynamic approaches, they simply don't work. And some known experimental works confirm this. In our work, we apply another approach called the incubation time approach. It's non-local in space and time. And in order to decide if there is fracture or not, one should just calculate this integral and compare it to some static value. It includes two parameters, tau, the incubation time, and d, the so-called, it can be treated as a fracture process zone size, or in fact, it is a scale level identifier. It tells us what's the minimal size of fracture. If we simulate crack propagation, it would be the minimal jump to the crack. And it naturally can be introduced into some numerical schemes, as the numerical schemes imply that we have some mesh, and that's why we have some minimal length, minimal sizes in our system. So it's very natural to take D as a minimal size, for example, the finite element. But for less, so to decide if there is fracture or not, we should select some area, look at the stresses acting on this area, integrate them using this expression, compare it to critical value, and if if the condition holds, there is fracture, and for example, if we do numerical simulations, we make the crack jump, or we eliminate the element or whatever, or we can actually use, for example, separation of elements using like Yuri, some maybe cohesive, we can write some cohesive law using these expressions actually. But let's turn to the crack initiation. Let's consider a semi-infinite crack in the unbounded space. We can use solve, and this crack is loaded by pulse, some function p, along all the length of the crack. We can solve this problem analytically using the potential method. And finally, for the case when the p is the Heaviside function, the step function, we can find an analytical solution for the stress intensity factor. But if we have the solution for the step function, we have all the solutions because we can use the convolution. So we can differentiate, we can use this convolution rule to find whatever, to find solution for any functions. And in our case, we're interested in functions of this type, of a rectangular pulse function. So the stress intensity will have this sorry. Yes, for the stress intensity will have this expression, the two rules, difference of the two rules with some coefficient, which is calculated through the material properties. All right. Since we have this stress density expression, we can substitute it to the version of the incubation time criterion. And we can find that according to this criterion, fracture can take place when the stress intensity already passed its maximum. So the stress intensity maximum is here. There can be fracture, but in some cases, fracture takes place in this zone. And we call this situation the fracture delay. So in terms of the load, fracture can take place here when the load is still active, or fracture can take place here when there is already no load. In this particular problem, it corresponds to the situation when the stress intensity drops, because here is T, the duration of our loading, here is T2. Okay. We made simulations for some experiments using this criterion. Maybe we used works by Kazarinov. For one of his set of experiments, actually there was no fracture delay. In this class, we show the dependency of the duration of the critical pulse on its amplitude. Again, we are loading our system with a rectangular pulse. So we are searching for critical values of these pulses which lead to fraction according to the incubation time model. And we get not one curve, but two curves. Of course, for this situation, the lower curve shows us the maximum delay situation. And this upper curve shows us the situation where there is no delay. If we look at the experimental points, they are grouped in this region, meaning that there is no delay. That means that the duration of the pulses which were used in these particular experiments were too low. So no fracture delay could be experienced there. But theoretically, the delay is still possible for this material. If we, again, according to the incubation time criterion, if we construct the dependence of the critical pulse duration on the fracture time, there is a region where this fracture delay is possible. So, but the same group of headed by Kazarinov actually did experiments where they saw the fracture delay. They confirmed that the crack can start when the stress intensity derivative over time is negative. So when the stress intensity already drops. So use this information and build the same curves using this only point, showing that it's the point of the fracture delay, and we constructed again these two curves. Again, this is the curve with no delay. This is the curve with maximum delay, and actually all the critical pulses, their parameters, lay between these two curves. So this is the instability. It's not for each amplitude of the load. There is a range of critical durations of the pulses, which lead either to no delay of fracture or to the fracture delay. And here, all the pulses from here, they don't lead to the crack initiation. So this is the zone of no fraction. Now, imagine the situation. You have a very simple system like this, simple mass on a spring, and you apply pulse load to the mass. Of course, due to inertia, there will be situations when pulses are not long enough, or the amplitudes of the pulses are also not high enough. For this problem, we can have, of course, we can have an analytical solution. We apply this type of load to our mass, and we construct the same things, the same dependencies as we just did for the crack. Here we construct dependence of the crack of the pulse duration on the fracture time, and the same thing for the oscillator, for the mass of the spring model. You see the expressions which govern these dependencies, they're totally different. But qualitatively, they are the same. Here we can have fracture delay when fracture time is higher than the pulse duration, and here too. Moreover, we can construct the dependencies of the critical of durations of the critical pulses on their amplitudes, both for the mass of spring and for the crack. They look very similar. So there is some motivation to build this very easy analogy between the crack initiation process and between the failure of the linear oscillator system. If we build another dependence of the impulse of the force which is applied to our system, we can even see more similarities between these two systems. There is a minimum of this curve both in the oscillator and in the crack. And we can even calculate the eigenfrequency of this virtual oscillator. So we try to show that we can formally attribute some inertia to the fracture process. And then actually the crack can behave as some system with inertia, and we can even calculate some virtual frequency of this process. We still don't know what does this frequency mean and what can be used, but we think it's kind of interesting. So now I move to the second part of my talk, where I will present another, probably a more simple approach from the discrete point of view to the fracture processes. Again, if we study the system, the linear oscillator loaded with short pulses, as we just did, we can find fracture delay phenomena. But if we study the loading of the system with the rising load, we can actually build a well-known strain rate dependency curves for this system. Again, it's due to inertia. If you load the system in a very fast way, like this alpha parameter is very high, there is some characteristic reaction time of the oscillator system. So we get this dynamic strength branch. And if you load the system slowly, you get the static branch or static strength of the system. So it's very similar to what we can observe in real materials. Well, if we get these two dynamic fracture effects, we can use this system to simulate some real experiments. Let's turn to well-known Ravichindra and Klaus experiments, where they build dependency of the initiating stress intensity factor on the fracture time. Our idea is very, I would say, straightforward and raw. We substitute the crack problem with the problem of the failure of the linear oscillator. So we actually cut some volumes in the vicinity of the crack. And we calculate mass of our oscillator. We calculate the applied force using the expressions for the corresponding stresses acting in this particular problem. And we calculate the string parameters, its strength, its stiffness, thinking of that our model should work in static conditions too. So we think that in statics, even fracture criterion works. And from this point of view, we calculate the stiffness of the spring and the critical deflection of the mass. And surprisingly, if we take this the size of this volume in the vicinity of the crack, which is more or less equal to the plate thickness, we get some nice fitting of the experimental results. Yes, we do not fit the static branch properly. We have to reduce the stiffness of the spring a little bit, but it is still remarkable. I mean, without any adjustments, we still get the effect. We get the dynamic branch for relatively high loading rates, and we get something like a static branch for the cases when we load with slow velocities. For another set of experiments, we managed to simulate the effect of the fracture delay in the crack initiation problem. So again, we use the same scheme. We cut some volumes as we treat as masses in the vicinity of the crack. We link them with a spring, and we managed to simulate some experimental points. And we even predicted, the regimes which are not tested experimentally, and we show that our model slowly goes to the static regime. In experiments, there were only dynamic regimes of testing, and we predict the static strength of this system. But for statics, we use finite elements to calculate critical pressure, which leads to the activation of the Irwin criterion. So finally, we also applied this technique for the spallation problem. It's the problem with the so-called undamaged specimens. It's the rod which is hit by some projectile, which results in a fraction from the other side, because your stress wave changes sign in the free boundary, and compression turns into tension. We virtually cut our sample into little oscillators, and then again we considered fracture of the oscillator instead of the sample. And again, we managed to adjust the mass and the stiffness parameters of the oscillator to simulate the strength rate curve, and we even managed to capture this little fracture delay, which is discussed in this paper. So, main conclusions. We managed to show that the dynamic fracture process can be regarded from a very, very simple, from a simple view. We can attribute some inertia to this process, and we can attribute some virtual oscillators to this process. And using this knowledge, we can build a very simple fraction model to simulate some real experiments. So that's it. Thank you for your attention. And for some, if you're interested a little bit more, there were two parts of this talk, and each part corresponds to a paper about this. Thank you.